Howdy and welcome back. We'll go ahead and wrap up this lesson by writing our first class in the C++ programming language. So I'll go ahead and specify kind of a blueprint for this, and then we'll begin kind of going through some implementations together. So you can see here that the definition of my color class is going to be laid out within the header file. We'll see here that there are a number of functions declared under the public access specifier, which will comprise the interface to objects of this type. In falling under the private access specifier, we'll see one, in this case, one member function, which will essentially be leveraged to support the implementation of our public interface. We'll also see three data members. Notice here that when we're talking about variables declared within the scope of a class, they are prefixed with this underscore here to communicate them as such. Following that, we'll see kind of a confusing declaration here. Static is essentially communicating that this variable is going to be shared across all instances of the class. So this will not be stored within the actual underlying representation of a color object. Instead, it will be put kind of in a global area such that all color objects can share it. Constant expression is saying that the value known for the variable that's being introduced will be known at compile time. Directly following that is going to be the type of object being declared, in this case an integer. And following the Google style glide, any sort of constant is going to begin with K, followed by the name of that variable, essentially using a capital letter to break up where spaces might occur otherwise. We can see here that we're going to characterize the max color value for all color objects is 255, as well as the min color value is 0. We'll see furthermore that valid color value will use these constants to ensure that any value that is being assigned to RG or B to check whether any value being assigned to RG or B is indeed a valid value falling within the range inclusive. So we saw a couple of declarations for member functions that will comprise the interface. What we've introduced is two different types of functions here. They're known as accessors and mutators. An accessor is simply going to be a function that's going to return the value stored within a private data member. In this case, R is going to return the value stored within the R data member. A mutator, on the other hand, is going to be a function that's going to store a value in a private data member or mutated state. In this case, we'd be passing RR and attempt to assign it to the data member R. What we'll see is that essentially enforcing that any sort of interactions or assignments to the data members are done through a mutator or another member of the public interface allows us to ensure that an invariant is maintained to ensure that, say, hey, anything that we're assigning to RG or B is going to be a valid color value. Obviously, right now, we haven't figured out how to enforce this on the construction of these objects. And we'll see that the values of the data members are undefined at the beginning of the object's conception. But in the next lesson, we'll actually go into, well, how can I construct objects with well-defined values? And then following this logic through accessors, mutators, or otherwise, simply ensuring that any member function of the public interface ensures that the invariant is maintained. So in this case, we're simply showing that, provided we had started with a valid color object, all functions thereafter, including the accessors and mutators, will ensure that these values are always within a valid state. So defining member functions, here's kind of how we go about the process. We're going to declare the member function within the class declaration. If the member function is a part of the interface, its declaration must be written under the public access specifier. If the member function is part of the implementation, its declaration must be written under the private access specifier. We will then go ahead and define the member function in the corresponding source file. We're going to prefix the name of that function with the class name followed by the scope resolution operator. And what we're essentially communicating is, hey, this is the definition of, in our case, colors function, whatever it might be, and not some other function. So let's go ahead and look at those definition here. The our mutator here is going to essentially check to see whether we have a valid color option, color value passed to it. If so, we'll make the assignment. Otherwise, we'll go ahead and throw a runtime error specifying that an invalid value was passed to our function. Notice the actual, go ahead and notice how we're actually specifying this. We're saying that colors are a function that takes an integer argument will be defined as following. Had we written void r int rr, notice that that is not providing a definition for colors are, but simply providing a definition for some function named r. It is extremely important to ensure that when we're defining a member function that we specify that it is that type's member that we're defining and not some other function out there. And that's what I mean by this. So we don't want to do that. We want to ensure that we're scoping these definitions accordingly. You can provide similar definitions for the G mutator as well as the B mutator. Then we can see for our simpler accessors, we're again going to say that, hey, the R that we're providing a definition for is going to be colors R function that has an empty parameter. Notice here that these are overloaded. So they have the same name, however, different ordering of their parameters. In the case of the mutator, single integer parameter, the accessor, empty parameter list, because we're simply returning a value. And that's what the definition is doing here. We simply return the value stored within the corresponding data member. You can see furthermore that I can define my private member functions just like I would for those comprising the public interface. I again have to specify that it is the color types function that I'm providing the definition for, and not say some sort of generic function that is not defined, not going to be a part of this type. So you might have noticed as we've been going through this that some member functions are postfixed with const directly after their parameter list, and if it's in a definition, directly before the opening brace. So directly preceding the call operator in both the declarations and definitions of my accessors, you'll see the keyword const. When const appears after, directly after the call operator, it's going to specify that the function will not change the state of the object for which it is called. So in this case, we are communicating here that R is not going to mess with the data members of the object it's being invoked for. What we'll see here is that if we're interacting with the object of this type through a constant reference or with a constant object in general, we can only invoke members on that object that are marked with const. This essentially allows the compiler to ensure that, hey, there are some functions that mutate the state, there are others that don't. If I'm dealing with a constant object, I should only allow the user to invoke those functions that have promised not to mutate the underlying state, because that is by definition what it means to be a constant object, and that will be maintained through a constant function. Now, these are just like agreements between us and the compiler. You can totally violate that, though you shouldn't, because it's, again, kind of breaking from convention. So let's go ahead and look at, how we could interact with this. So we create a new color object, C. Notice at this point, the data members have undefined values. And we'll see that a constructor will allow us to set this with actual reasonable starting values. But right now they're undefined. So let's go ahead and just make an assignment to, let's say, C's R data member. And we'll go ahead and do that using the mutator. So I would go ahead and write C.R and provide the value that I would like to initialize the R data member with. Thereafter, I can go ahead and access that data member and indeed confirm that that assignment happened. To do that, remember, I can't access those data members directly. Instead, I would use the accessor to view their state. We do that by simply writing C.R. Notice here the output is indeed 255. Let's say later on I'd like to go ahead and update this object's R value. I could go ahead and use my mutator again, this time passing in the value 11. I could again use the accessor to confirm that this assignment was made, or to otherwise use it in some sort of other expression. But for the sole purposes of the illustration here, I'm just writing the value to standard output to show you that indeed, hey, the state of the object changed. R went from being 255 to 11, and we confirmed this. And to go ahead and finish up this lesson, I want to go ahead and show this additional example, how we can ensure that whenever an assignment is being made to any of our data members, we could ensure that a valid value is indeed being assigned to them. So in this case, I can go ahead and make an assignment to C's R. I'm going to do that through the mutator, and I'm going to confirm it by just printing the value out to standard output. Here I can see that, okay, R did take on the value of 255. Excellent. Now let's go ahead and say I inadvertently, forgot that it was between 0 to 255 inclusive, pass in 256, or for all intensive purposes, this could be any value larger than 255, or any negative value. Notice that when I hit pass in this invalid value, if you remember, according to our definition, a exception would be thrown. We verify that here. Whoops. When we attempted to pass in what we considered an invalid value for the R data member, an exception was indeed thrown. So we'll kind of put this together in the next lesson by showing that, hey, from start to finish, so throughout the lifetime of objects of our user-defined type, we can actually enforce invariance on that such that the object is always within whatever we define to be a valid state for objects of that type.